where he currently serves as the Dean of the School of Engineering and the National Sciences. Professor Arslan is very famous in the industry and the academic society, especially in the physical layer wireless communications. So without further ado, please join me to welcome Hussein for the second part of this talk. Thank you.
Okay. All right. Thank you, Shanyang. It is again an honor to be here, and thanks for the invitation. It's great to be with you all. I'll share my screen and then get started right away.
Sure.
I hope you can all see my screen now.
Yes.
Okay. All right. So this is, like Shanyang said, this is part two of my seminar series. The title is Back to the Basics for to the 6G, reinventing OFDM. So OFDM, as you all know, has been used in 4G and 5G. And over the last several years, the research community, including my research group, has been studying several alternatives to OFDM, including OTFS, AFDM, and many other alternatives. But eventually, standards started last year. We are also attending the standards and contributing to it. And at the end of the day, as I mentioned in my previous talk, OFDM is the baseline of 6G standards. So that's why I said reinventing OFDM. OFDM has been very popular, as you all know. We always think that maybe there is nothing more to do in OFDM. It's very well established. But in my talk, actually last time, I mentioned that even though OFDM has been used for 4G, 5G, even Wi-Fi, WiMAX in several standards, it comes with a lot of issues, especially with the vision of 5G. I discussed about some of the issues. That's why the talk is reinventing, because we really need to look at the OFDM if this is going to be the waveform that we will be using in 6G, due to many reasons. One of the reasons is for also a wide variety of channel conditions. So it has to be, it has to work everywhere at any given time. That's why, we didn't want to take the risk of replacing OFDM with alternatives, and we stick with it as a baseline in spite of all these problems that we mentioned. So that's the reason why we are reinventing OFDM. So I just wanted to clarify that issue. If you review, I think before I get started with the details, so those major issues that I discussed with OFDM, these are some of the summaries. One of them is, which is very critical, is the energy efficiency of OFDM, which is related to peak to average power ratio, which is very high in OFDM. And we need to fix this problem right away. Otherwise, OFDM, again, which will be in 6G, and one of the major themes of the 6G is energy efficiency in all the aspects. And OFDM doesn't fit with the spirit of 6G unless we fix this problem, peak to average power ratio. Of course, peak to average power ratio can be caused due to the modulation, due to the waveform, and there may be other reasons why we have a large peak to average power ratio, like pulse shaping as well. So I'll discuss about that. I'll spend some time on this thing. This is something that we really need to fix. Another major issue in OFDM is, even though we think that OFDM is robust to synchronization, but if you go deep, OFDM has a lot of issues when you lose synchronization, time synchronization and frequency synchronization, and also uplink ranging. So this is another issue that we need to fix and improve these techniques, synchronization techniques, ranging techniques, uplink ranging techniques, end-to-end compatibility of OFDM and unification of NTN and TN using, again, the mother waveform of OFDM has some issues that I discussed. Doppler issues with extreme mobility, like satellites, they're moving extremely fast. And in the past, Doppler was not considered as a big issue, and we compensated the ICI, inter-carrier interference, due to the Doppler using adaptive modulation and coding techniques. But if you use extreme mobility, like satellites, this problem also needs to be fixed. Another major issue in OFDM is channel estimation, channel prediction, channel feedback, and we need channel for equalization, for MIMO coding, for many reasons. And the standards are getting more and more complex, and everything that we add requires additional pilots and new pilot design. And pilots are taking over the data and occupying too much spectrum. Therefore, we need to come up with a new pilot design techniques, channel estimation techniques, channel feedback mechanisms, if you want to use OFDM and DFT spread OFDM as the mother waveform. And related to many of these things is multi-connectivity. So in the future standards, 6G and beyond, we are expecting that a user is going to is going to be connected to multiple transmission points simultaneously, and some of these transmission points could be satellite, and a satellite transmission point and transmission point can serve a user simultaneously, but that's not possible with the OFDM waveform, and we need to find solutions for this. Either, again, improve OFDM, or we need to come up with alternative waveforms. So this is a problem that needs to be solved. Out-of-band radiation has always been an issue in OFDM because of the sync pulses. Even though we applied windowing and filtering techniques to suppress those side lobes, but still, of course, it comes with some trade-offs. When you apply windowing and filtering, it is not coming for free. So those trade-offs needs to be readjusted. And how do we apply windowing? How do we apply filtering? Whether it's going to be in sub-carrier base, sub-block base, or whole band base, it needs to be revisited. And flexible band operation is one of the major thing in 6G. Coexistence with other technologies like radar technologies, coexistence with the previous standards, with 5G standard, and backward compatibility are also issues with OFDM, especially if you're using multi-numerology OFDM, we're going to have issues. And as you all know, 6G comes with ISAC, integrated sensing and communication, and the new standards need to support more sensing applications, will have more sensing capabilities, and we need to make sure that OFDM is suitable for sensing as well. If there needs to be some improvement on OFDM, we need to study that as well. Regarding to energy efficiency, we already discussed about peak to average power ratio in terms of improving the energy efficiency in the transmitted signal, but we also need to make sure that the receivers are energy efficient. Processing of the signal at the transmitter and receiver is energy efficient, and the future standards like 6G needs to support more of those IoT devices, and some of these IoT devices, they don't even have batteries, like backscatter devices. So that processing and also supporting those low cost, no battery type of devices using OFDM signal is problematic, because if ambient signal is properly designed to support those IoT devices, then we can get a better system performance. So we'll talk about some of these things in this talk. And last but not least is the AI and ML, integration of AI and ML into the new standards, including physical layer. When it comes to physical layer, again, how do you use AI ML to improve channel estimation, to improve equalization, to improve waveforms, to improve the physical layer parameters adaptation are critical things that needs to be studied further. So let's start one by one and discuss some more details of these things, these issues. And I will try to, finish everything within an hour. I may not be able to, even though, again, this is my second presentation, but the problems are so wide, so rich, so there are so many details, so it's not really easy to cover all of them within an hour. But I'll try my best to at least tackle with some of these issues. One of them is, like I mentioned, is rethinking the reference signal design. Reference signal, I mean pilot signals, training signals. And these signals, as you all know, are used for estimating the channel, extracting some parameters related to channel. And the channel knowledge is used for a wide variety of reasons, even though many of you are using channel for equalization and also for CSI feedback information. But really, if you look at how we use channel in the past, there are so many. How we use the pilots in the past, there are so many reasons actually, including physical layer security, including sensing, localization, sensing, tracking, including radio environment mapping. So in addition to those classical reasons why we use pilots for channel estimation, for equalization, beamforming, MIMO detection, link adaptation, scheduling, etc. So the need for understanding the channel with the new standards are increasing because the new standards are becoming more and more adaptive, more and more intelligent, and we need the intelligence, the adaptation comes with some knowledge, okay, with some knowledge about the channel, about the users. So the more we know, the better we can do. So the optimization of the network, optimization of the transmitted signal, optimization of the physical layer parameters, waveform, modulation, coding, pulse shaping, anything that we use to build the signal. If you want to do the right job, we need to know more about the channel, more about the user, more about the environment. So, and also the interference. So the more that we know, the better that we can do. But that knowledge comes again with the pilots and with the sounding, okay, the channel. So the question here is, in the past, we transmitted the pilots along with the data because in the past, the pilots are only needed to equalize what the channel did to the signal. So understand the channel at the bare minimum and equalize the signal, the received signal, so that we can demodulate the data. So that was the main goal. Therefore, we always associate the data together with the pilot in the same domain. But today, the goal is different. We don't estimate the channel only for demodulation, only for equalization, but we estimate the channel because of all the reasons that I mentioned, okay, including, again, sensing, ISAC. So therefore, the question is, now that we have more needs and more details of the channel information, where do we transmit the pilot and where do we transmit the data? Do we have to transmit them in the same domain? Or do they have to be orthogonal with each other? Can we superimpose pilot and data? And how do we do this? And why do we do this? Again, when we are doing sensing, communication, and physical layer security, because security, physical layer security also requires a detailed channel knowledge, not like we did in the past, the bare minimum. Now we need more details. The better the details that we have, the better, more security that we can have, more sensing that we can have, better, channel estimation, better channel knowledge, better environment design. Okay, so from that perspective, there is a question that we always ask ourselves: should we disintegrate pilot and data? Do we use different frequencies to transmit pilot and data? Do we use different cells, different antennas? Do we use different waveform for pilot transmission and for data transmission? And all these things are questions that we need to answer. So if you look at history, we just going back very old days in the second GSM and also American Digital System, and also 2.5G CDMA structures. If you look at the training symbols or pilot transmissions, like I said, it is in between, in the middle, or in the beginning. If it is in the middle, we call it mid-amble. If it is in the beginning, we call it preamble, post-amble, or in between the data. So we always find a way to transmit, optimally to transmit the pilots, and then where to transmit them, how many of them that we need to transmit, what is the level of redundancy. It's a design criteria. It's an engineering design that we developed. So this has been done even in the long ago. And in every standard, actually, this is something that we rediscuss. Okay, how do we transmit the pilots? But like I said, it's always along with the data in different form. Okay, with different numbers. So if you go to OFDM, these pilots are transmitted in 2D compared to the previous standard, which is pilots are added in the time dimension as a symbol, pilot symbol or training symbols. So in OFDM, it's spread in 2 dimensions over the OFDM symbols and over the OFDM subcarriers, so that we can get the channel knowledge in 2 dimensions. The data is also transmitted, as you all know, in a grid, 2-dimensional grid. So pilot is spread in between the data. In Wi-Fi, for example, the pilots, because Wi-Fi is the mobility is low, we don't spread it all in 2-dimensional. We transmit the training sequences, OFDM symbols for sampling the channel, and then data symbols, and then every once in a while we transmit those training symbols. But in cellular, since the mobility is high, we need to really spread all these pilots in 2-dimensional and then do 2-dimensional interpolation. And there are other ways of, again, inserting the pilots. Of course, this is like time frequency. Like I mentioned earlier, we don't have to transmit the pilots in always time and frequency. We don't also have to transmit them along with the data. So what are the options? You all know, we can transmit them in the delayed Doppler domain, the lattice. We can transmit them in other domains, the sequence domain, chirp domain. So these are some of the options that we have already studied. But when we were studying these things, we didn't really study them from a channel estimation perspective, from actually, again, communication perspective. So we always thought that, pilots should be in the same domain where the data is transmitted. For example, if you look at the delayed Doppler domain, some of these grids can be pilot grids, and the rest could be data. So we always thought that the data and pilot should be in the same lattice, in the same domain. But actually, it doesn't have to be that way. And one good example for this is DFT spread OFDM. DFT spread OFDM is used in 5G, as you know. And this is a single carrier waveform compared to OFDM, which is a multi-carrier. But we can generate that single carrier waveform as like a OFDM signal. This is classical OFDM. And when we apply a DFT spreading, so the data is in time domain. And then when you get the data, like let's say that M data symbols, and then when we apply DFT spreading, and then we map them to OFDM carriers, and then do classical OFDM modulation with endpoint FFT, IDFT, and then we have this time signal. So if you look at this time signal and then compare it with the original symbols, actually we can see that these symbols are going to be reappearing in time, okay, depending on how you map them, whether they are mapped as blockwise or interleaved wise. You can see that these data symbols are going to appear in time, okay, whether if it is block allocation, then we'll use some more samples because we have now n samples compared to m samples. So there will be more samples, and there will be original data samples, but along with some other samples that's created by a linear combination of these data samples. Again, if it is interleaved, then these samples are going to appear in different way. Okay, but at the end of the day, the data is in time domain, but a spreaded version of this data are mapped into the frequency domain, the frequency carriers of OFDM, and the channel is estimated in this domain. Even though data is transmitted in time domain, the channel is estimated in frequency domain because we apply frequency domain equalization. So equalization is done in this domain. So the equalization is done in frequency domain, but the demodulation is done in time domain. So clearly you can see that the channel and the data are not in the same domain in DFT spread OFDM. So this is an example. So it's like, let's summarize it. Data is in time domain, equalization in frequency domain, pilot is also in frequency domain. So in 5G, pilot and data is transmitted in different IFFT blocks. They are interleaved because since these data are spreaded here, so if you just remove some of these samples and then replace them with pilots to estimate the channel over this block, you are spoiling the DFT spread OFDM structure. So that even though that's something that can be done, but in 5G, what we do is we transmit the pilot in some IFFT blocks and data in some other IFFT blocks. So we need to make sure that those pilot transmissions and data transmissions are designed in such a way that the coherence time of the channel, sampling of the channel in all multiple IFFT blocks are properly done depending on the mobility. So alternatively, we can puncture some of these samples because this is a spreaded data. We can puncture them and then replace them with pilots and then estimate the channel over here and equalize these samples and then go back to frequency domain. And this is basically showing how we can do that puncturing and replacing them with DMRS pilots. And then at the receiver, we first estimate the channel using DMRS from these samples, and then equalize the signal in frequency domain, and then do endpoint IDFT, and then demodulate the data at this point. So these are basically things that we can do in DFT spread OFDM. As I mentioned, again, the data and the pilot transmission, in this case, they don't have to be in the same domain. I mean, it could be in the same domain, even though we don't do this. You can transmit pilots along with the data in DFT spread OFDM. But why would I do that? Because I need the channel here, not there. and I need to do equalization here in the frequency domain, not there. But alternatively, you can do that like we did in the single carrier systems. You can add pilots here, do the channel estimation, and then time domain equalization. But that's more complex. The reason that we use OFDM, because OFDM allows us to do frequency domain equalization. Time domain equalization becomes more complex, and you use like nonlinear equalizers. That's why we prefer to transmit pilots in frequency domain and then deploy equalization in frequency domain as well. So, like we did here in classical OFDM, we have these pilots, and then there is this channel, and then this is the receive signal, and then using the pilots, we sample the channel, and then by doing some interpolation, so we find the channel along the data points, and then we equalize the receive signal over the whole band, and then we demodulate the data. But if you look at here, in the frequency domain, the channel is correlated. So the channel is slowly changing. And if you add pilots in every subcarrier, then it is redundant. So therefore, we need to transmit pilots to make sure that we have enough pilots so that we can do proper interpolation. So when it comes to interpolation, of course, there are different ways of doing the interpolation. One way of doing this interpolation is, get those samples in frequency domain and interpolate using linear interpolation. Simple interpolation is linear, but it's not the best. Or alternatively, you can take these samples, which are correlated, even these samples are correlated, and then apply a transformation back to delay domain, because the in delay domain we assume that the channel is sparse compared to frequency domain, which are correlated. So when we transfer them to delay domain, we get those channel impulse response with different delays, and these channel components are independent of each other, and that reflects basically how many taps that we have. And then we apply a windowing, and then we go back to the frequency domain to smooth the channel in frequency domain. So the question here is, what is the best transformation? So, in the classical OFDM, we do DFT-based transformation to transfer them to time domain. What is the which is the domain that represents the channel in the sparsiest form? This is a question that we always ask ourselves. Also, another question that we ask ourselves is, which domain is the domain where the channel is more stationary? Okay, so if you look at the frequency domain, this domain, okay, the channel is, we have so many components, it's not sparse, definitely. But not only that, if the receiver or transmitter moves a little bit, then the channel changes, okay? So channel is not stationary. So we are not only looking at the sparsest representation, but we are also looking at the most stationary version of the channel, and that whatever domain is going to give us the stationary channel parameters, that we are seeking that domain. So the long story short is best dictionary, okay, and least number of parameters. And compressed sensing is something that we have studied in the past. Basically, if we have measurements of anything, but in our case it's channel measurements, and if these channel parameters are correlated in this domain, like in OFDM, this is frequency domain, and we are trying to seek a domain that can represent the channel in the least number of parameters and then in the most stationary way. And then that transformation, in this case, is represented by A, but in the case of OFDM, we use DFT matrix, okay? This A is the dictionary. It's a transformation matrix. So we need to find the best transformation matrix so that we can find the channel in its sparsest form, okay? That's basically what is compressed sensing all about. So in order to find the best dictionary, so rather than assuming that DFT matrix is the best dictionary, we need to ideally search for it, okay? What is the best dictionary to transform the channel into its sparsest form? But so far, if you look at our studies, most of the researchers, they use Fourier transform-based dictionaries, and we use IFFT, FFT, or fractional Fourier transform, or discrete Fresnel transform, or simplistic Fourier transform like in OTFS. Okay, so in those cases, basically, probably this is something that you have seen in almost all the waveform presentations. So basically what we do, we look at the channel in various domains. This is, for example, the channel that represents the channel impulse response, time-varying channel impulse response. But if you do a Fourier transform, we can get the time frequency response, which is basically OFDM. If you just take this channel and then apply a simplistic Fourier transform, we can get the delayed Doppler response. So this is the reason why actually OTFS has been suggested as the ultimate waveform, because the channel is assumed that it is in its sparsest form in this domain, because the channel can be represented by delays and Doppler values in its sparsest form, and also it's assumed that the channel is stationary, relatively more stationary compared to the other domains. That's why OTFS has been used, has been suggested as an alternative waveform. And you can see here this delayed Doppler response of the channel, and then you can also see how sparse it is compared to time frequency. For example, in the delayed Doppler 1 bit, if you just take that simplistic Fourier transform, it can spread to whole time and frequency. So if you look at here, in the delayed Doppler, you have 4 taps in time, but in time frequency, it spans all the time and all the frequencies. So this is actually in a more sparsest form. So just taking this a little bit further, this representation of the pilots in different domain, delayed Doppler, time frequency, affine, and Doppler frequency and time. And if you look at different waveforms, and if you transmit, for example, pulses in that domain, for example, in OTFS, if you transmit a pulse-on in the delayed Doppler domain, how that pulse-on appears in time frequency is like this, spreaded. And in the affine domain, again, it's not sparse, and Doppler frequency response and time response. So you can see how they appear in different domains. Similarly, if you take a look at the AFDM chirp in affine domain, it appears a very sparse pulse, but if you look at the other domains, it will be spreaded. So if you look at that, OFDM time frequency DMRS signals that we use, they appear in some carriers or some OFDM symbols. But if you look at these pulses that we transmit, DMRS pulses, pilots, let's call it that way, in the delayed Doppler domain, they are all spreaded. So I think this summarizes the story of where to transmit these pulses, whether it should be in time domain, frequency domain, delayed Doppler domain, whether they should be along with the data or it's a different domain than data, is a question that we are trying to answer. Similarly, we can use other transforms rather than Fourier type of transforms, Walsh-Hadamard transform, Euler transform, and multi-carrier CDMA. In multi-carrier CDMA also we spread the data along frequency carriers and along also OFDM symbols. Depending on that, we have these multi-carrier CDMA waveforms. And spreading sometimes can be helpful But sometimes, again, it may have some negative effects. So whether we spread or not spread is a design parameter. So it's not always, we can't always say that spreading is better. Sometimes, focusing and doing actually, transmission in a very focused way in a specific domain could be better. So that's basically what I'm trying to say here. And these are some of the spreading examples. And another thing that I want to mention, something that we always miss, our researchers, we always focus on medium channel, but at the end of the day, at the receiver, what we see is not the medium channel. What we see is the effective channel. And effective channel doesn't represent the exact channel, the actual channel. So in the effective channel, we have so many factors. You can think of it, effective channel, as like a temperature. Okay, there are temperatures actually, especially in places where the humidity is very high. The thermometer, what the thermometer measures, and it's like a, how do you feel the temperature felt like. So similarly, in communication, when we look at the channel, how do you feel the channel at the receiver? What is the channel that you measure at the receiver? Depending on the synchronization errors, depending on the pulse shape, depending on the waveform structure, this is going to be different than how the actual medium appears. Okay, so at the end of the day, what we see, what we observe, is the effective channel. Okay, and then that effective channel depends on the waveform, depends on the pulse shape, depends on the synchronization error, whether in time, frequency, depends on the RF front end, transmitted receiver, especially the filters that are used, depending on the noise, depending on the channel model that you use. So if you assume a different channel model, because this is an assumption, you don't know what the channel model is, how many taps the channel has, you all initially make an assumption. You say that this is the channel model, and based on this channel model, this is going to be my channel estimate. Okay, that channel estimate is maybe like it is estimating noise as the part of the channel, because you are over modeling the channel. You are assuming that your model is not the exact model of the channel, but you are over modeling. So when you over model the channel, and the effective channel estimate is going to have different estimate than the actual channel. So all these things are going to affect what you see compared to what is actually out there. And there are some examples actually that I have shown here. For example, if there is a timing offset in OFDM signal, actually the channel is going to be in frequency domain. So I'm only showing the frequency domain channel response with and without timing offset. So if there is no timing offset, if you only assume one tap channel, just for the sake of simplicity, if there is no timing offset, there will be a flat channel response. The amplitude is going to be flat, and then the frequency is going to be also the same. Okay, it's not changing. But if there is a little bit timing offset, then there will be this timing offset will reflect as a frequency rotation in frequency domain, and then the phase of the channel is going to be changing linearly. But if you don't know that this change is caused by the timing error, because you assume that timing is perfect, and then you think that this rotation, this change, is due to the channel. Actually, the change is not due to the channel. It is because of the mismatch. And if there is more timing error, then this rotation is going to be faster. And then the pilots will start estimating the channel as if this rotation is caused by the channel, even though, like I said, it is caused by the timing offset. Similarly, other things can also affect the channel estimation. So therefore, we have to be very careful. Many people are assuming that when they are designing a receiver, they assume that perfect synchronization, everything is perfect. Therefore, even having integer delays and fractional delays will have an impact on the estimation of the channel. So if you have integer, for example, in OTFS, this is very popularly known now. If you have integer delays and Dopplers, then the channel looks sparse, but when the delays are fractional, the effective channel, what you estimate, is going to be much richer. So it's not going to be a sparse channel, and you cannot control the channel delays. Actually, the channel delays, you cannot guarantee that it's always or Doppler values are going to be integer. So it can be any arbitrary value. So we have to be careful about that. So how do we use channel information? Again, one reason that we have used channel information for communication is for equalizing, and also lately for pre-coding, MIME pre-coding. But lately, with 6G, we are also using channel information for sensing and file security. So these are some of the things that we have used in the past for channel estimation for radio environment measurements, RSSI, RSRP, SINR, CQI, channel state interference measurement, strong beam measurement. So these are all from channel knowledge estimation. And of course, we use these estimates for link adaptation, mobility management, adaptive scheduling, interference coordination, etc. And there are other possible measurements that we can do. For example, dominant versus non-dominant interference estimation, channel estimate, channel impulse response, channel frequency response, location or direction of interference estimation, sparseness of the channel, estimating how sparse the channel is, line of sight, non-line of sight estimation, blockage estimation, mobility estimation are some of the things that can also be used from the channel information. Some of these measurements are going to be short-term in the form of microsecond to second. Some of them are longer term, and some of them are very long-term measurements. So let me move the second topic, which is the energy efficiency. Energy efficiency, again, in 6G is the number one topic here. So one of the main requirements of 6G is we need to make sure that we have this energy efficiency as a parameter, KPI, key performance indicator, in every aspects. So in terms of transmitted power, in terms of processing power, and how much energy that we use for overhead and redundancy, how much energy that we use for control signaling. So we are trying to improve in every aspects. So these are some of the things that we use in communication where it consumes a lot of energy. For example, transmission energy, signaling energy for pilot synchronization, monitoring energy, for sensing and monitoring, infrastructure energy for base stations to be active, and processing energy, computation energy for signal processing and algorithms and things like that. So we use energy in every level. For the sake of waveform, OFDM, peak to average power ratio is the main thing that energy consumption adds up. And so the reason that we have high peak to average power ratio, because OFDM is this is OFDM time signal. It is some of those sinusoidal signals with the random data added on all these. So independently modulated subcarriers, these subcarriers, they add constructively and destructively. And then occasionally, with this coherent addition, we can have these large peaks. And then if you look at the dynamic range of this OFDM time signal, it has a very large dynamic range and causing very large peak to average power ratio. Even though PAPR is used very popularly, but we use CCDF as a better measurement of dynamic range of the OFDM signal. CCDF is the cumulative, complementary cumulative distribution function. Basically, it provides all the statistics of the time signal, and using these statistics, actually, we can measure whether the signal has a better dynamic range compared to OFDM. For example, that dynamic range changes depending on the number of used subcarriers. So if you have larger FFT sites, and if you use all these carriers to populate the data, random data, then the CCDF gets shifted to the right, and our goal is to shift them to the left. So the reason that we want very low dynamic range, because the power amplifiers are nonlinear devices, and because of that nonlinearity, it compresses the signal, the peak signals, clips them if it exceeds some threshold value, saturation point, but it also compresses the signal. So at the end of the day, the output of the power amplifier will not have a linear amplification. So it will have non-linear amplification, causing in-band interference and also out-of-band regrowth. So these are two major problems. And out-of-band regrowth, is causing adjacent channel interference, and it also causes intercarrier interference, especially when you are using multi-numerology techniques. In-band interference is something that you cannot do anything about it because it looks like a noise, a white noise. So we need to solve this problem in OFDM, and there are so many techniques that has been proposed in the past to reduce that peak to harsh power ratio. But many of those techniques comes with a lot of penalty. So in terms of spectral efficiency, in terms of complexity. So even though, like I said, so many techniques are proposed, it saves the energy from transmitted power, but it creates energy problem in the processing. So at the end of the day, we are not really gaining much by using OFDM. So the important points regarding to peak to harsh power ratio, it's a waveform dependent. So OFDM probably is the worst waveform in terms of peak to harsh power ratio. So you can change the waveform to minimize the peak to harsh power ratio. But it's not only waveform dependent, it's also modulation dependent. Depending on the type of waveform, it may be heavily caused by modulation or pulse shape or data formation. Even MIMO procoding can impact the peak to harsh power ratio. So it's not a single dimensional problem. It's a multi-dimensional problem. It's a joint problem. Even in the standard right now, there are two groups in the standard are working. One group is the waveform group. The other one is the modulation group. Both of them are actually trying to minimize peak to harsh power ratio independently, but they are not realizing that these two problems are joined. Okay, and so they need to work together to solve this problem. So, like I said, it can be due to the waveform and modulation, and the peak to harsh power ratio for OFDM and DFT spread OFDM are not the same, and the cause of the peak to harsh power ratio is also not the same. Okay, so there is always this trade-off. I mean, if you are trying to fix this problem, it comes with a lot of redundancy and complexity. And we always want to have receiver agnostic solutions. So if you are doing a technique to solve peak to harsh power ratio, but if the receiver needs to know what is done at the transmitter to reduce that peak to harsh power ratio, then that causes another problem, because you need to transmit that information, whatever you did, whether it is a manipulation that you did at the transmit signal, that information needs to go back to the receiver so that the receiver can undo to that manipulation. And in the standard, we are looking at DFT spread OFDM in the uplink, because in the uplink energy efficiency is more of a problem. The reason that we are looking at DFT spread OFDM because it has better peak to harsh power ratio, but it is not ideal. Also in DFT spread OFDM, as I mentioned, the modulation and pulse shape has more impact on peak to harsh power ratio compared to CPU OFDM. In CPU OFDM, modulation has less impact, pulse shaping has less impact, but it's, like I said, it's a sum of sinusoids, random data that causes that large dynamic range. But in the DFT spread OFDM, we don't have that sum of sinusoids as much as OFDM. Therefore, there are other reasons that causes this PAPR. So if you look at DFT spread OFDM, it has two options. One of them is a block allocation. So this is the DFT spreading. This is the data in time domain. This is after the DFT spreading, we map them to OFDM carriers. We can map them localized manner. We can map them in distributed manner. Depending on the mapping, also we have different PAPR. So don't think that DFT spread OFDM has the same PAPR no matter how we map this data. So at the end of the day, we have PAPR problem whether you use OFDM and DFT spread OFDM, but the solutions are not the same. The cause is not the same. If you know what causes the PAPR, then we can come up with different solutions. For example, in DFT spread OFDM, one of the most popular solution is applying shaping, frequency shaping, FTSS. So in frequency domain, after mapping all these spread data into carriers, so we have this extended spectrum. We can do extended or non-extended. So the easiest way is to extend spectrum extension and then apply a window over these carriers. And then when you apply the window in frequency domain, the time domain signal is going to be more shaped, better shaped compared to a sync pulse in time domain. Now we have lower side lobes. And if you have lower side lobes, then the PAPR is going to be better in time domain. So in DFT spread OFDM, one reason that we have large PAPR is because of these side lobes. So therefore, if you want to reduce that side lobes, we need to reduce that. If you want to reduce the PAPR, we need to reduce these side lobes. So, another reason in DFT spread OFDM, the PAPR, why we have a high dynamic range is the modulation, which wasn't the case in classical OFDM, because we can ignore the modulation effect in classical OFDM, but in single carrier systems, the modulation effect cannot be ignored. Therefore, we use pi over 2 shifted BPSK or pi over 4 shifted QPSK or some other shifting mechanism, so that these are the classical techniques we used in the past, like in second generation systems, so that those transition from zero crossing is not going to happen when we do the shifting. So these are some of the techniques that we use. Another technique that has been used by Ana Garcia, one of our friends and collaborator, is FM-OFDM. Instead of transmitting OFDM signal, time signal, directly to the power amplifiers, so you do an FM modulator, because FM modulators are constant envelope. So basically, when you redesign OFDM into an FM OFDM, you can just make that signal, OFDM signal, with this manipulation as a constant envelope signal. And then if it is constant envelope signal, then you can transmit it through power amplifier without any large dynamic range. But of course, this also comes with some other issues, because the time signal has to be a real value signal. In order to have a real value output of OFDM, you need to have conjugate symmetry in the frequency domain. That means that you are going to be reducing the data rate by half of the classical OFDM. Another problem is when you apply frequency, the spectrum also gets expanded. You occupy more spectrum. So from frequency efficiency, spectral efficiency perspective, we lose a lot by using FM-OFDM. But from a power efficiency perspective, again, when you have this constant envelope, you gain. So energy efficiency, like I said, is not only caused by the transmitted power. There are other things that we also try to satisfy the energy efficiency. One of them is low power wake-up devices. So along with the main radio, we also associate another radio, wake-up radio. Also along with the normal data signals, the OFDM signal that we are transmitting, we are also generating a wake-up signal. So this, as if we have now two radios, two signals that a base station transmits in the downlink. Similarly, in the uplink, radios can transmit wake-up signals and then to wake up the base stations. So base stations can sleep, radios can also sleep when they are not talking. And then during this sleeping time, we have to transmit some signals to maintain the synchronization. We call them wake-up signals. Wake-up signals are used for maintaining the synchronization, but with extremely low power mode. Also, wake-up signals are used to wake the main radio when there is information coming in. Okay, so similarly in the uplink we also have the same goal. So wake-up radios, wake-up signaling has initially first considered for Wi-Fi in the Wi-Fi 7, but later in release 19 we implemented wake-up radio, okay, as a part of the energy-saving modes. In 6G, this effort is going to continue. So this is an important topic, especially for IoT devices, low-power devices, but also even for the regular phones and regular devices, because it will reduce the power consumption significantly. So how do we generate wake-up signals from OFDM signal is a critical research area that we have been studying. So we don't want to have another transmitter, another signal, another waveform to generate this low power, low cost wake-up signal. So we want to use classical waveform, which is OFDM in our case, and we need to really manipulate the OFDM transmission so that it can generate the classical data signals, plus it can also generate wake-up signals. For example, it's shown here. Some of the carriers are used as the wake-up carriers, wake-up signal carriers, and the other carriers are used the classical data new radio transmissions. So we are mapping those wake-up signals into the spectrum carriers, and then the output of this OFDM has regular signals plus also some on-off keying, simple on-off keying signals. And these on-off keying signals are going to be easy to receive, easy to synchronize, and then easy to process at the receiver. So that's the main goal. But the question here is, OFDM is the best waveform to generate alternative signals, low power, low cost signals, or do we need to look at other waveforms, okay, for wake-up signaling and for wake-up radio concept? So this is like some of the things for future directions and challenges, alternative waveforms that can meet, okay, these requirements for low data rate, medium data rate, and low complex receivers, and exploiting wake-up signals for localization and positioning, and also integration of this wake-up concept with other networks as well, and things like that. Another energy efficiency aspect is ambient IoT. Ambient IoT is also a very important topic. So similar to wake-up radios, ambient IoT devices, they don't have RF front end and analog to digital converters. All these classical radios have. They are very low power, low cost devices. Possibly if they don't even have battery. So, but they need to be able to process the signal, ambient signal. Ambient signals are the classical signals that we transmit for our main receivers, but these signals are also used by ambient IoT nodes to add some extra information on the top of these ambient signals so that the receiver can receive and process them. So that's the idea. The question here is, if I am going to design a signal, a waveform, that is useful, that's optimal for a classical receiver, okay, legacy receiver, but also that signal should be suitable for a low power, low cost device, backscatter receiver, to process on that signal, to add additional information on that signal, of course with low data rate. And what is that signal is the question that we have been asking ourselves, okay? Of course, OFDM is the legacy waveform, and how do we use OFDM to generate a signal that's useful for these ambient IoT devices is something that we are studying. But alternatively, what is the best waveform out there where this waveform is optimum both for legacy networks but also for ambient IoT networks? So this is the question that we have been asking ourselves, and we are trying to find solutions. As I mentioned, these devices are they don't have oscillators, they don't have analog digital converters, they don't have this RF front end, they are low power, they don't have battery, and so we need to jointly design the waveform, tag reflection strategy, and receiver algorithms if you want these ambient IoT devices as part of our network. Okay, so these are some of the research directions for ambient IoT: waveform design, interference management, synchronization, framing, random access mechanism, and so on and so forth. So last energy saving topic that I want to say is the network energy saving, which is related to what we have discussed earlier. It's also related to the waveform, and all these highlighted areas are part of the waveform design, frame design, pilot design, data structure, and intelligent sleeping modes when we are some of the base stations on and off when we make them sleep, and how does it affect the network performance, beamforming, and all these things are also related to energy saving and waveform design as well. So these are the things that that's how waveform, okay, traditional waveform design and 6G energy native waveform design, and how do we do this in the past and how should we do it for the future are some of the research topics that we need to study. One last topic that I want to discuss before I finish my presentation is the out-of-band radiation. And as we all know, OFDM is not really the best signal in terms of the ambiguity function and how the compactness of the signal. If you look at the out-of-band radiation of the OFDM signal, because of these sync pulses, they are very heavy. Of course, when we look at the carriers in band, we don't care about these sync pulses because they are all orthogonal. But if we lose the orthogonality, of course, we started worrying about this because they cause ICI within the same band. But if we have multiple numerologies, if we have alternative, waveforms, multiple waveforms, multiple numerologies, all these out-of-band radiation becomes very meaningful, very important. For example, you see that here in multi-numerology OFDM, this out-of-band radiation is creating internumerology interference. This is one of the reasons why we think that multi-numerology OFDM didn't work in 5G because of this out-of-band radiation. And of course, you can apply windowing and filtering to suppress this energy, or you can add some guards in between. But again, these are solutions, but they create some other problems. So it doesn't come for free. In 5G, we developed a new duplexing scheme, which we call it subband full duplex, using OFDM compared to classical FDD, where the receiver and transmitter frequencies are separated by a very large channel spacing, so that the side lobes of the receiver and transmitter are not going to impact each other. They are not going to cause duplexing interference. So this is what we did. But in frequency allocations, we don't have this kind of pair of spectrum, and we don't also have the opportunity of separating this transmit and receiver links far from each other. So instead, we propose that the community proposed that we can have subband full duplex. So this is like OFDM bandit and number of carriers. We can divide these carriers into downlink and uplink carriers. Okay. And then by this way, we can just transmit we use some carriers for downlink, some carriers for uplink. That's why it's called subband full duplex. So we divide the OFDM band into subbands, okay, and then use these subbands for the uplink and downlink compared to classical full duplex or compared to classical FDD. The problem with this subband full duplex again goes back to this side lobe problem. I mean, like, it's a beautiful strategy, but they are not orthogonal. Downlink and uplink are not orthogonal anymore. The delays are not also controlled, and synchronization and all these issues are causing this leakage from downlink to uplink, uplink to downlink, especially if there is this near-far problem. and causing a huge interference, cross-link interference. So this is one problem that we are trying to tackle in 5G, especially with the release 19 and afterwards. So in 6G, this problem is going to continue unless we figure out a solution for this out-of-band interference. And again, out-of-band interference is related with OFDM. So it is a problem of OFDM. And either we need to fix this problem and keep OFDM, or we need to replace OFDM with something else with minimum, out-of-band radiation. So, it's for the moment, OFDM is the waveform that we decided. So it's going to be the baseline waveform. If you want to use sub-band pull-duplex with this baseline waveform, we need to come up with mechanisms to reduce this out-of-band radiation. And windowing is the classical technique, but if you use windowing the way that we use, it comes with another penalty, which is the spectral efficiency. So we need to come up with a better windowing techniques, better filtering techniques to fix this problem. With that, I'm going to close my presentation, and then if there are some questions, maybe I can just entertain your questions. Thank you.
Thank you, Hussein, for this great talk. Yeah, sorry
Okay,
that
so
we have a limited time
I'll stop
duration.
sharing.
It's okay.
I promised that it will be 1 hour, so hopefully, I
It's all
fulfilled
good.
my promise.
Yeah, of course.
All right. So
Yeah.
it's so many topics. Sorry about that. I have to browse through, all these things very quickly.
No, it's very good to have this comprehensive view, especially from the industry perspective, because this is what we are lacking, especially for the academias. Yeah, so we also have some questions that I hope you have the time to answer. The first one is about this discussion you mentioned that for pilot and data, they somehow they do not have to be in the same domain, right? Do you have any guidelines or in general some insights on which domain suits better for under what channel conditions for this for data and pilots?
Yeah. This is something that we have been studying. Several of my students are looking at this topic. I can't say that I have solved this problem. So, it's a very complex problem.
Yep.
First of all, if you transmit data and pilot in different domains, whatever, is compressed and localized in one domain, it spreads to other domain. Let's assume that you are transmitting pilots in delayed Doppler domain.
Mm-hmm.
And then data in time frequency domain in OFDM. So all these pilots are going to be overlapping with the data, so interfering with the data. So that's why I also mentioned that do we have to have pilots independent of the data, okay, orthogonally, or do we have to make them superimpose on each other? Okay, so this is, for example, one thing that we are looking at. For example, from sparsity perspective, the channel. I mean, again, even though I mentioned that we need to find a better dictionary, but so far we can assume that the delayed Doppler domain is the domain where the channel can be represented in its sparsity form and more stationary form. So, and estimating the channel there is going to be easier for us because really you need to put pilots and then you need to see how they are spreading in the delayed Doppler domain,
right?
Rather than actually estimating them in time frequency and then mapping them to a like we did in the DFT-based channel estimation. You can directly transmit them in that domain and then in data in another domain. So this is one option, but again, that there is this superimpose and then the interference issue that we are trying to solve.
Right.
So anytime, again, even though I suggest that they have to be in different domain, but whatever you do in different domain there, you're gonna have to face with the interference. So whatever is local here is gonna be spread there. Okay. So if the data is local in time frequency, when you go back to delayed Doppler, they are gonna be spread. Okay.
Exactly.
So the data is gonna interfere with the data, with the pilot.
Yes.
So again, these are the things that we need to look at. It is not really, I mean, I don't have a very clear answer. I mean, I have to be honest with you. So this problem is not solved yet. So it needs a
Yes.
lot of research.
Right.
Because it is a new concept. Okay, it's a new concept, and I don't even know whether that is the way that we should do. It's just a question that we are asking. Okay, I'm not saying that data and pilots should be disintegrated. I'm not suggesting that. I'm just asking the question: should we look at this? And we are looking at it, and then again, it doesn't come for free. It has
Of course.
some issues that needs to be tackled.
Right, right. I totally agree. I also have another question related to this, especially when you were during your presentation, you mentioned that what we see is effective channel. It's not actual channel that we're interested in. But I think in sensing, most of the time we are interested in the actual channel, in the sense that we need the delay and Doppler.
Exactly.
Yes. So do you have any insights on the difference between the effective channel and the actual channel, and how, say, filters and other operations can mitigate or change these regions? Thank you.
Excellent question. In the past, we didn't worry about the differences between effective and medium, because we never cared about what is the actual channel. We only cared basically how this channel, the total channel, the effective channel, disrupted my signal. Because at the end of the day, whatever the effective channel, that is the channel that your data sees. Okay.
Yes.
So you wanted to remove that effective channel from the data, and you didn't care about the medium. But the importance of the medium just came recently because of the sensing, because of physical air security. So now we need to remove everything else, okay, that affects this effective channel from from the received signal, so that I can only focus on the medium. Okay. And some of these things are stationary. Okay, you can learn in time, and then you can see if it is a linear processing. Okay, if the effective channel is the convolution of the transmit receiver filter, or if it is basically some other effects. If you can learn them, you can deconvolve, and then you can basically go back to the original channel.
Right.
But really, that process by itself is very difficult. And also, some of these things are not linear, so it can also have some nonlinear process. So that's where AI comes into the picture. Remember, like we always think, what is the best use case? Possibly AI can be used to figure out how to get back to the exact channel, the real channel from the what I measure. Okay. Or you can go and then do that transformation that I mentioned. So imagine that the effective channel is the channel which is basically not sparse anymore. Okay, effective channel has
can be dense.
lots of correlations. Correlation can come from the filter, and then now how to take that effective channel, apply a dictionary to it. Okay, apply a transformation to it. Again, most of these transformations again are linear, but if you can generate a transformation, even if it is linear, and then go back to medium, that could be a solution. Okay, but if there are some non-linearities, then I guess that AI can be utilized. Again, I'm just throwing out ideas, but these are the things that needs to be studied. But the problem is very clear. The problem is I measure only effective channel. Now I need to go back to find the actual channel from it, and there is a need for that.
Yes, thank you. Okay, another question I have received, that you have mentioned that for DFTS, OFDM, and OFDM, there are still going to be the waveform for 6G. Do you think it will be possible for the industry to consider some sort of non-orthogonal alternatives, such as faster than Nyquist or some packing waveforms, in order to boost the high data rate?
Yeah. Yeah, that's also a very good question. Actually, that's my, in terms of research, that's the area that I love very much. Okay, non-orthogonal waveforms. Okay,
Right.
GSM was non-orthogonal waveform. I discussed
Mm-hmm.
about that in our last seminar.
Right.
And we decided that non-orthogonal waveform should be used because we already knew that, okay, the channel was going to disrupt the orthogonality of those sync pulses. Okay, originally, actually, in the narrow bands, we started with orthogonal waveforms, and then when we increased the bandwidth to more than coherence bandwidth of the channel, and then we realized that this channel is gonna disturb the orthogonality anyways, and then
Exactly.
the effective channel due to that disturbance is going to be much longer, because if you use something, okay, and then that orthogonality is lost due to a reason, and then if you look at the effective channel and the need for equalization, it becomes disastrous. So
Mm-hmm.
so you better go and then fix your problem and then use non-orthogonal. That's why we use GSM, and then we make a compact pulse shape, and then
Mm-hmm.
assume that orthogonal transmission should be there, and the channel is going to disturb my signal anyways. So the total effective channel is going to be more limited compared to Nyquist pulses that used in the past. So
Mm-hmm.
similarly, when I look at our communications, when I look at our problems, like now things are becoming so, like in OTFS, for example, like
Mm-hmm.
you have studied OTFS as well,
Of course.
and then we always assume that the channel is very sparse, okay, and then
Mm-hmm.
everything is going to be orthogonal. Non-orthogonal is going to be caused by delays and Doppler shifts, and then the total number of taps is going to be like 3 is coming from Doppler, 4 is coming from delay, 7 I can do a very simple equalization, okay, to
Right.
compensate. But when you add that fractional things, all of a sudden the channel becomes fatter and bigger. Okay,
Right.
so
Right.
in that case, we need to go back and then look at the situation again. Okay, when you have now this situation, should we focus on orthogonal pulses, on orthogonal waveform, or non-orthogonal waveform? I think eventually I am leaning towards non-orthogonal design
Mm-hmm.
rather than orthogonal design, because
Right.
it's becoming more and more difficult to maintain orthogonality anymore.
That's true.
So if we push, okay, things to be orthogonal, the penalty and the computational complexity at the end of the day, the effective channel that you observe is becoming more. So maybe I think we need to go back and redesign our waveforms so that we allow some non-orthogonality.
Mm-hmm. Thank you very much. Another question I want to follow up actually is because we have been discussing waveforms, especially during your presentation, but I don't think we have touched too much on MIMO. Actually, in our last presentation on Charles Park, there was one researcher proposed this idea using, for example, massive MIMOs to do strong beamforming to kill some of the unnecessary multipaths, such that you can have a relatively easy channel to deal with. Do you think will be a new design insights, for example, from the industry perspective, that we can somehow help the waveform design by using bigger arrays in MIMO?
Yeah, I think that's an interesting and very good approach. I mean, like if you have massive MIMO, you can eventually convert that channel, selective channel, and then to a non-selective channel. Okay,
That's true.
so eventually, actually, the need for equalization can be avoided. I mean, we always think that we use OFDM because there is a need for equalization. Frequency domain equalization is the simplest one. That's why we want to use OFDM. But everything actually, started with the need for low equalization. But if you don't need equalization, if you
Mm-hmm.
can solve this problem, okay, by multiple antennas or by other mechanisms, I mean, MIMO you are suggesting, but it could be other mechanisms, then
Mm-hmm.
that affects our waveform design as well. You understand what I'm saying? So then
Yes.
we need to go back because that problem is already solved. Now I need to look at the waveform design from a different perspective.
Yes. Thank you very much. Okay. The last question I have received from the
That's
audience.
why I think
Mhm.
I,
Yes,
I,
please.
I believe Yeah, that's why I believe that when the waveform design, now that MIMO is there, okay, and the number of antennas are increasing, it's part of our life. We cannot just design a waveform independent of the antenna design. It has to be together. I mean, like, for example, we are saying that DFT spread OFDM in the uplink. DFT spread OFDM in the uplink is good, okay, but if you're using one antenna, if you're using pre-coding, okay,
yes,
and then if you have massive number of antennas in the uplink, I mean, right now we don't have massive number of antennas, but eventually if you have, 4 antennas, 8 antennas, all the gain that you had, okay, because why do we use the FT spread OFDM? Because peak charge power ratio is low. But when you apply pre-coding in the transmitter, now you are going back to the same original problem. Antennas are creating that new peak charge power ratio. You understand what I'm saying?
yes,
Therefore,
exactly.
all the gains that you get with single antenna is lost now with the multiple antenna systems.
Yes. That's actually related to my next question. So this PAP bar is not just that can be designed in some modules individually. It's a joint problem. But do you think it will be possible for the industries to really create say a group that focusing on this joint process to deal with the PAPR issue, considering the waveform, antennas, and other aspects?
Yeah, I mean, why you ask very good questions to the point. I mean, very very detailed. I mean, as I mentioned in my presentation, even currently now, all these companies, like big companies, like very intelligent engineers working in these companies, do you ask them to study PAPR separately as a modulation group, focusing on the PAPR by doing constellation, geometry, shaping, or probabilistic shaping? The focus is just to reduce PAPR, okay, by shaping the QAM constellation in a way that it's gonna reduce, but independent of what the waveform is used. Okay, you can't do that because these two things are correlated with each other. Okay,
Exactly.
I mean, like, people are using like DFT spread OFDM again. As I mentioned in the presentation, waveform, modulation, pulse shaping, MIMO, everything are interconnected with each other. So if you just look at them as different designs, okay, and then focus on them, without thinking what is the effect of the others, then you are going to be in disaster. Okay.
That's true.
So I think eventually we need to look at them all together because they're all tied together.
Right.
I mean, whatever PAPR technique that you use in DFT spread OFDM, if you apply it to OFDM, that's not going to work because the cause is not the same.
Right.
If you change the modulation, okay, whatever constellation, whatever shaping that you do, that won't affect OFDM, okay, because the cause of PAPR in OFDM is not due to the modulation. I mean, it may have an impact, but other things have more impact than the modulation.
Exactly.
Okay, and then pulse. So it is very important that you understand all these details and then relate them to each other.
Right. But yeah, I agree with you. This is somehow missing in the current industry and academic research. But it is also a good opportunity for us to pick up and really solve this problem. Yes. Okay. Thank you, Hussein. Because
I mean, like, the thing, like, I'm lucky in the sense that I have students working in modulation, students are working on waveform. Therefore, I had to relate all these things. But if if your focus is on waveform, probably you are missing everything else. Okay. If your focus is only MIMO and antenna design, and if you don't know anything about waveform, anything about modulation, probably you are missing, the big picture. So I think it's very important that we understand the big picture.
Exactly. Thank you very much. Because of the time limitation, we have to close our presentation today. And I would like to thank you, Hussein, again for the second time for the presentation at the Charles Park. And if we have some further questions from the audience, please drop me or Hussein an email, and we'll be happy to address them. Okay. Thank you again for joining us.
Thank you, Shuang. Thanks for the invitation. Okay, have a nice day.
You too. Bye-bye.
Bye.